So it says started. Let everyone know they are being recorded. Yes. Okay, thank you.
Okay, no, thanks. Good evening, ladies and gentlemen. For those that
Yeah,
have,
good
Good
evening.
evening
How
to
are
you
you?
too, sir.
yes. For those that are joining us for the first time today, if there are any people who are new, let me just repeat our ground rules. I will be going through the lesson slide by slide. So you all will be muted. You will switch off your mics, all of you. But if you feel that there's something that you need to ask when I'm explaining something, you just switch on your mic and speak. I will not be able to see hands if you raise up your hand or whatever. I'm not going to see that because I'll be seeing the screen that you are seeing on your side. So today's lesson is about mostly application of differentiation and basic integration. So I will do a few questions on differentiation. And then I have got more questions on integration by popular demand because there were people that were saying that it is the one that challenges them the most. So I will have a little bit more examples to deal with on integration. Right, so your mics are off now and I am starting. Um, this is a typical application of differentiation on the issue of minimum, maximum, and a point of inflection. So if maybe a question comes like this, it says determine the minimum, maximum, and point of inflection. So we need to find the minimum point, the maximum point, if they both exist, because there are some functions that may have only the minimum, others will only have the maximum, and then other functions do not have a point of inflection, others do have. So we are going to investigate this function y equals x plus 1 over x, if indeed it does have all the three points. Now, before maybe we can even start with this one, I can just do a background explanation about what is meant by minimum or maximum. Minimum and maximum are if you go to a normal graph, maybe of power of 3, it will be coordinates of turning points. So the turning points, there are two types. The one is a minimum where it's a U-shaped part, the way the graph is U-shaped, and then maximum is part when the graph is N-shaped. So now to get these two types of points, minimum and maximum, it's about the first derivative of the given function. You find the first derivative of the given function, you put it equals to 0 and solve for x or the unknown. Now the value of the unknown that you find are x coordinates of either the minimum or the maximum. Now to find the y coordinates of those x coordinates, you take those x values and you come back to this original equation, y equals to x plus 1 over x, put the x values there and calculate y values. Then you get what we call coordinates. A coordinate contains an x and a y coordinate. Then there is a point of inflection. Now, a point of inflection is a point where the graph changes its concavity. So when a graph is U-shaped, at the part where the graph is U-shaped, the graph is making what we call a concave up, because the curve is caving upwards. If it's N-shaped or the maximum, then the graph is doing a concave down. So where that concavity, the turning up and the turning down, where it changes, it's called the point of inflection. And it is usually between, if it's more especially if it's a graph of power of 3, it's usually between the turning points. So now there's another thing that you may need to note is to check whether a turning point is a maximum or a minimum. If you've got already the turning point itself, before you even sketch the graph, even if you are not sketching the graph, you can be able to check whether the point is a minimum or a maximum by using the second order derivative. So firstly, to find the point of inflection, you do a second order derivative and you put it equals to 0 and solve for x. The x that you find in the second order derivative when it is equals to 0, it is the x coordinate of the point of inflection. If you want to check whether the previous points that you found are is a minimum or a maximum, you take that second order derivative itself. And in the derivative, you substitute the x coordinates of those points. If it's a minimum, when you substitute that x coordinate on the second order derivative, if it's a minimum, you will find that the result is positive. The number that you find out when you put x, the x value of a point which is a minimum, it produces a positive number. If the point is a maximum, when you put the x coordinate of that turning point, the result of the second order derivative will be a negative number. That's how you check whether points are maximum or minimum. So that is the theory behind what we are going to do in this question. And when we start with this one, definitely we will have to find the first derivative of this expression. And then you find that derivative, and then you will change that 1 over x to x to the power of -1 for easy reference in terms of doing a first derivative. And the first derivative is you take the power of the x, multiply it in front, and from the exponent, you subtract 1. Do the same with the second term. Take the power that is there, which is -1, multiply it in front, and from the exponent, subtract 1. And that gives you the derivative. Then at maximum and minimum, that derivative is first derivative is equals to 0. And then the derivative is done as I have explained. That is why you are having on the left side 1 minus x squared. 1 is coming from the power 1 of x, multiplying in front, you get 1 x to the power of 1 minus 1, it will be x to the power 0. Then x to the power 0 is also 1. So 1 times 1 is 1. That is where you get this 1 from. Then you go and do the same with the second term. Take the negative, that is the power minus the -1, multiply it in front, you get -1. And from the exponent, you subtract 1, you get x to the power of -2. Then you get 1 minus x to the power of -2 equals to 0. Then you need to solve for x. You have got various methods that you can use. You can take minus x squared to one side and raise both powers to the power 2. But that one, it can be mistaken. You can do mistakes because you will only, you may think that the final answer is only the positive one. So I would like to caution you there. I think the best way is to make powers positive. So which means that you will rewrite this x to the power of -2 as 1 over x squared and multiply everything by x squared. After you do that, you will get x squared minus 1. If it is like this, then there's no mistake of having only one answer. If you can take 1 to the right side now, then and you want to take the square root both sides. When you take the square root of x squared, it will be x because x is a variable. But when you take the square root of 1 on the right side, it has to be plus or minus. That is what you must never forget. But to avoid that, you can just maybe factorize x squared minus 1 because x squared minus 1 is the difference between two squares. When you factorize that, you get x plus 1 into x minus 1 equals to 0. And therefore, the x values will be plus or minus 1. So which are those values of x? Now, these values of x are x coordinates of turning points of the given function. Now, as I have said, to get their y counterparts, then we are supposed to take x equals to 1 and go back to the original equation, put x equals to 1 here and x equals to 1 there. And then you will find that this will be 1 plus 1 over 1. 1 over 1 is 1, then 1 plus 1 is 2. And then you do the same. X is equals to -1. You go and put it there, -1, and you put -1 there. Then you'll get -1 -1. So y for x is equals to -1 will be -2. And the points will be 1 is to 2 and -1 is to -2. Now, the thing is, we don't know now which one of these two is a minimum and the other one, which one is a maximum. And then we can use that test that I have mentioned to check which one is a minimum and which one is a maximum. And to do that, we will need the second order derivative. And that second order derivative, so it means that now it will have two functions. One function, when it is equals to 0, it will be your x coordinate of the point of inflection. When you take that second order derivative and substitute this one on the second order derivative and get a positive answer, it means this is a minimum. If you take this one, put it here and get a negative answer, it means this point is a maximum. So now we have got our second order derivative, which we do on the first derivative, which is this one. So we come to this first derivative and we find its derivative. And the derivative of 1 is 0. And the derivative of minus x to the power of minus 2, it will be minus 2 times the coefficient, which will become positive 2. X to the power of the exponent minus 2 minus 1. And it gives us this one, which is 2x to the power of minus 3. So this is our second order derivative. Now, to check for maximum and minimum, let's do that first. Let's check for whether this point is a maximum or a minimum. This one is a maximum or a minimum. Then we will get to take only the x value of the point, which is this one. Put it in place of x on the second order derivative. When we do that, we get 1 to the power of minus 3. And 1 to the power of minus 3 is the same as 1 because it is 1 over 1 to the power of 3. So 1 times 2 is 2 and 2 is positive. Now, by virtue of this being positive, it tells us that this one is a minimum turning point when this is negative. When this is positive, it tells us that this is a minimum turning point. And then to check the other one, we do the same. We substitute x by minus 1, and then we will get that minus 1 over, it will be 1 over minus 1 to the power 3, which is minus 1 times minus 1 times minus 1. And eventually the answer will be negative. And negative, it means that the turning point, I have made a mistake here. I've made a mistake. It should be it means the turning point minus 1 is to minus 2 here, not 1 is to 2, because we're checking the second one. The first one is checked there, up there, and it's complete, it's done. So it is the point minus 1 is to minus 2 that we are checking. Here, the signs should be minus 1 is to minus 2 for this one. Pardon me about that. I forgot to put the negative signs here. It is the second point that we're checking here. Then finally, we want to find the point of inflection. So we must take this second order derivative, put it equals to 0, and solve for x. So when we do that, we will find that 2x to the power of 3 equals to 0. It means x is equals to 0. Then we find that the point is 0 is to 0, because when we take this x equals to 0 to the original equation here, we put 0 there and put 0 there. 0 there, it means that this does not exist. But I have tried to check how come do we have this point 0 is to 0 as the point of inflection. Thou, the value of y cannot be found. Here, the value of y, you cannot find it here because 1 over 0 is undefined. But the truth is that this is the point of inflection. So what I did with this question, I went and drew this graph to see how it looks like. Then it will explain indeed that this point 0 is to 0 is indeed the point of inflection. Let's check how the graph look like. This is how the graph will look like. The graph is a graph that comes here and turn here, as we have said, at the point minus 1 is to minus 2. It makes a maximum turning point as we have predicted. But now it comes here and does an asymptote with this y-axis. It means that it does not touch the y-axis. And this graph here on the other side has got a minimum there. And the graph makes an asymptote with the positive y-axis. It does not touch the y-axis. But now the question is, where does now this concave down? Because if you can check this other side, the concave here is down. So like from concave down, and now we come to concave up. Where does this change in concavity happen? It happens exactly here in between the 2 points, in between minus 1 and 1. And between minus 1 and 1 is the point 0 is to 0. Although the graph doesn't pass through there, but that is where the graph changes from concave down to concave up. And that is why this still is our point of inflection in this case. Is there any question?
I'm good,
Silent
day,
means,
sir.
oh,
Good
yes.
day, sir. How are
Yes.
you?
I'm good, and you?
I'm good. I'm good. I've just joined this class right now, and I,
Okay.
I think that I might have missed some of the sections that you have covered.
No,
So,
that was the first example. You may have missed the previous session, and it is going to be uploaded tonight. So ma'am will Dr. Dlamini will upload the first lesson that we did on Monday together with this lesson that we are doing today, so you can be able to go through the lessons again.
okay, yes, yes. So I was just looking at, like that question that you were busy with right now before you can even show the graph,
Oh, here.
Yes, yes, yes. Here, when you have to determine your minimum, your maximum, and point of reflection. So you're
Yes.
given that equation, okay? So that equation, yeah, you've simplified the equation. Now, when it comes to at the maximum and minimum, obviously you derive, right?
Yes.
So from there, I can see that y is equals to x plus x to the exponent 1. You have derived it into 1 minus x to the exponent negative 2, ne? Which is fine. Then
Mm.
now you have actually put it in order to say that, okay, s squared minus 1 is equal to 0. So from there, yeah, I do understand that how you determine your x equals to 1 or x equals to negative 1. I do understand that point. Ne? My
Mm.
question is that these points, the points were one and two, ne? And
Mm.
then one, -1 and -2. How did you
Yes.
even determine those points, those
Oh,
coordinates? Mean to say.
oh, the coordinates. Yes. Oh, no, a very good question. Let me explain it that very quickly. So these x values that we have found here, x is equals to 1 or x is equals to -1, are x coordinates of the turning points. Now, the
Okay.
turning point has got an x coordinate and a y coordinate. So the x coordinates are these two, which you can see here, the x is 1 and here x is -1. To find this y value, you go back to the original equation, which is this one, and you put your x is equals
Okay.
to 1 for x there. So when you put x equals to 1 here and x is equals to 1 here, this becomes 1 over 1.
Mm.
And then 1 over 1 is 1. 1 plus 1 is 2. That is where we got this 2 from. Then you do the same with -1. Put -1 here,
Okay.
-1 there. Then -1 plus 1 over -1 is -1. So -1 minus 1 is 0. Sorry, so -1 is 2, which is this one.
Two. Okay. All
Yes.
right. Okay. Oh, okay. So, okay. Now I do understand how you calculated your y values, which is you substituted those x values to the given equation on top, ne?
Yeah, the original one, not to the derivative.
The
Not to the
original
derivative. You
equation,
do it
yes.
to the original equation. Yes.
And then um that second derivative, ne? What is it
Yes.
for?
So the second order derivative, we find it to find the point of inflection and to use it to check whether the points that we found, which is this one and that one, whether they are maximum or minimum. When you substitute the x coordinates, which is this one here and this one there, for the first point, if you substitute 1 here, you get an answer that is positive. An answer that is positive show us that this point is a maximum. Sorry, it's a minimum. And if you substitute x here and you find an answer which is negative, it shows that this point is a maximum. So if you
Oh,
remember, where do
yes.
we get this information from? So if you remember parabolas, the graph of the
Yes.
form y is equals to ax squared plus bx plus c.
Yes. I
When
remember.
a is positive, you always get a minimum turning point. You get a U-shaped graph.
Yes. Yes.
So if you take that graph and you do the first derivative, the first derivative in ax squared plus bx plus c, the first derivative is 2ax plus b. Now, that is the first derivative. Now, the second derivative is 2a. So it means that the sign of a determines whether the point will be a minimum or a maximum. Now, in the parabola, When A is negative, the graph will be N-shaped. So it will be having a maximum turning point. So that is why we get this information from that. If you take the value of X, put it in the second order derivative, and you find a positive answer, that positive answer tells you that that point that you are testing is going to be a minimum turning point. And then the point with the negative signs will be a maximum turning point. And then that is why I had to go and do this graph so that we can check if we are on the right track. And indeed, we found that we are on the right track. This one that has got negative signs is a maximum, and that one with positive signs is a minimum.
So that second derivative, you actually derive the first derivative, right? After deriving the first derivative on the equation. So this one minus x.
The first derivative is this one.
Yes, the
1
first
minus
derivative.
1 minus x to the power of minus 2. Now, what is the meaning of d squared y dx squared? It means it's d over dx of dy dx. So it means that this is the derivative of the first derivative. So we call this one the second order derivative. So we do the derivative of the first one.
Okay.
Right.
Noted.
Right. So shall we move to the next question?
Yes, you may. Thank you.
Okay, then you may switch off your mic and then you can switch it on again if you have got another question. Right. The second question, as we have said, we are doing the applications of differentiation. The other question can come in this way. It can say an open metal tank is to be constructed on a square base to contain 32 cubic meter of a liquid. Now the question says, find its dimensions so that the surface area of the tank in contact with the liquid may be a minimum. Now we need to first understand the question. In this question, we are having a metal tank with a square base. So if it's a metal tank with a square base, it's like a box. So this box, and they say it's open on top. So it means that this box has got a base which is a square. It means that on the base, it has got all four sides equal. Then it has got the height on the sides to become a box. So it means that around that square, there are four vertical rectangles standing on this square base, one on each side of that base. And then the top, it's an open space because they said it is an open tank. So this box has got 5 sides. There's the 4 rectangles on around it, and the base that is sitting on it, which is a square. And if we can put it as a diagram, it will look like this. Now, if you can look at this diagram, this is a 3-dimensional diagram standing on a flat surface. So it can be confusing. So let me explain it. So if this is the base of this box, where the box is sitting on, and you are looking at this box tilted a little bit so that you can see underneath, this is the bottom part of the box. So because they said that this box have got, it's a square, it means that the 2 sides are equal. So I've named one side X. So the other one will also be X. We were not told about this height, so we don't know the height. So I've just mentioned, I put it as H. So this height is the height of this box, which means that the rectangles that are around this box are this one that is here on one side, and this one that we are seeing here that is facing us. And for this one that is facing us, there is another rectangle on the other side that we cannot see. And then this one on the side as well. There is another rectangle on the side that we cannot see. So which means that the rectangle that has got this X and this H and this one has got an X here and an H. There are 4 in number. And then on top, which is the top side we cannot see, it's open there on top, according to this explanation. I hope this diagram makes sense and it's connected to the statement that we are given there on top. If not, you can maybe ask, I can explain. But then if there is no question, then we can continue now. Now they say this box that we have got here in this picture contain 32 cubic meters of a liquid. So we can ask ourselves, what does this 32 cubic meter represent? Can anyone tell me, what do you think that 32 cubic meter represents?
It represents
It represents the volume.
It is the volume of this container, isn't it? So
Yes,
from
sir.
that fact, it means that we are going to have two equations in this problem. We will have one equation that has to do with the volume that we are given here, and another equation will have to do with what we are being asked. We are being asked about the surface area. So we'll have a formula for volume. As you have mentioned, it is indeed the volume, and the volume of a container, rectangular container like this, will be area of base multiplied by the height of the box, which is this formula that is here, V equals x squared h. X squared is the area of base, which is this part, and then h is the height of the box. Then, but this has been given, the volume is given as 32. So we replace V by 32 and get an equation 32 equals to x squared h. And we stop there because that is the information that we get until this full stop. Now we need to come and now take care of the second part. The second part says we must find the dimensions so that the surface area of the tank in contact with the liquid may be a minimum. Now, firstly, we will need to first find the equation that describes the area of this box. Now, as I have said at the beginning, this box contains 5 sections. The first section is the bottom section, which is the base, and the area thereof is length times breadth. Now, length times breadth will be x times x, which is x squared for the base. And then there are 4 rectangles that are standing up. And those rectangles that are standing up, each one of them, the area is length times breadth, which is x multiplied by h. So we've got x times xh 4 times. That is why the area of this box will be area equals 4xh plus x squared. Now, the question says we want to find this, we need to find the dimensions of this tank. So the dimensions, it means that we need to find this value x and the value h for this area to be a minimum. Now, as we have said in the previous example, the word minimum or maximum, it means that we want to find the value of the unknown when the derivative of whatever we are being asked about, in this case is the area. The derivative of the area must be equals to 0. Now we have a problem. The problem is that our equation contains 2 variables. Now, to do a derivative here, we are not sure whether we're supposed to say dA dH or dA dx. We're not sure whether we can say dA dH or dA dx because we've got 2 variables. Now, this is where the volume comes into play. The volume also contains an equation containing x and h. So we take one of these 2 variables, x or h, and make it the subject of the formula from the volume equation, so that we can come to the area equation and replace that one variable. Then after replacing that one variable, we will have now our area in terms of one variable. That is when we can start doing the derivative. Now, when we go to this equation, 32 equals to x squared h, we look at either x or h, and we ask ourselves, between the 2 variables, which one is easier to make the subject of the formula? And you can see that indeed it will be h, because if we try to make x the subject of the formula, it will involve the square roots, and we don't want to do that. So to avoid having square roots all over the place, we will make h instead the subject of the formula. So when we do that, we will find that h will be equals to 32 over h. Over x squared. H is 32 over x squared from this equation. Then we come to the area equation and replace h by 32 over x squared, which is this bracket that you see there. The rest of the things are exactly the same. 4x is the 4x that was there on the original equation. The x squared is this one that you see there. So then in place of h, we have put its equivalent from the given volume there. Then from there, we just simplify this equation. And when we simplify, we will multiply 4 by 32. We get it's 128. And then x divided by, in fact, it will be x over x squared. Then x over x squared is actually 1 over x. And when we take that 1 over x up, it becomes x to the power of minus 1. And then plus that x squared. So our equation for area in terms of x only becomes now a equals to 128 x to the power of minus 1 plus x squared. Then we want to find this area to be a minimum, as we have done in the previous example, minimum or maximum. At maximum or minimum, the derivative of a with respect to x is equals to 0. So then we now go to the equation and do its derivative. The derivative is the normal differentiation. You take the exponent that is there, multiply it in front, and then from the exponent, you subtract 1. And then you do the same with the x squared. You take the 2, multiply it in front. From the exponent, you subtract 1. And you eventually get minus 125 x to the power of minus 2 plus 2x, and that equals 0. Then from there, you need to solve for x. Because we've got negative powers there, we have got minus 128 over x squared plus 2x. Multiply everything by x squared to get our equation as x. It will be actually minus 128 plus 2x to the power 3. Then if you can take minus 128 to one side and divide both sides by 2, you get x to the power 3 equals to 64. And x to the power 3 equals to 64. 64 is the same as 4 to the power 3. So if x to the power 3 equals 4 to the power 3, it means x equals to 4. So now we have found one dimension. Now we know that for this box to have a minimum area, this x must be 4. So it means also this must be 4, this must be 4, and that must also be 4. Now they say dimensions. So which means that we also need to know the height of this box. To find the height of the box, after we find that x equals to 4, we go to the equation that contain x and h, and it will be the volume equation, because the area equation does not have area. We don't have that area yet. What we only have is this volume equation that has got a 32 cubic meters on the left, and now we've got this x squared h, and then we can replace this x by 4. When we replace this x by 4, 4 squared is 16, and we solve for h. We divide by 16 both sides. We find that h must be 32 over 16, which is 2. I'm sorry. Now we know the dimensions. So maybe another examiner may say, find the minimum area. It was not asked in this question. So what do you do now to find the minimum area? Now that you have got x and h, you go to the original equation. A is equals to 4xh plus x squared. Replace every x here by 4 and every h by 2, and you can find that minimum area of this box. But here the question stopped at finding only the dimensions, which is finding the values of x and the value of h. And this question is done. Shall we now move to the next application of differentiation? Now, this one is a question that says, if x is equals to x squared cos y plus y squared sine x, determine those. Now, the d that is cursive like that, the d that is cursive like that is only used when we do partial differentiation. Now, what is partial differentiation? Partial differentiation is the same way how we do derivatives normally. But when you want to do a derivative of this function z, now z is a function of two variables in this case. That is the difference between this kind of an equation and other equation. Other equations will be having y equal to, and everything else on the right hand side will be x or a function of x. But here we have got two variables. variable x and variable y. So now when we are doing a derivative of this equation with respect to x, we are supposed to use this cursive d to show that it is partial a derivative with respect to x only. Therefore, whatever we see as y everywhere else, when we are doing a derivative with respect to x, that y is regarded as a constant. So you regard this y as a number. So it means that you don't do any derivative on y. You do only derivative on the axis that you see on the right side. If you are doing a derivative of this z with respect to y, and you use this cursive d, you are going to consider every x that you see in here as a constant. So x will be looked at as a number. Then the only variable that will be counting will be y. Then you use the cursive derivative d, cursive derivative d, like the one that you see on this diagram. Now this question says they just want us to find the 3 second order derivatives. There can be a fourth one. The fourth one can be d squared z over dy dx. Then these two values will be swapped. And then you will see how we do this. Then you can also be able to go and find the partial derivative of z with respect to dy, and then d multiplied by dx at the bottom. So for us to do these second order derivatives, we definitely need first order derivatives first. Now, even if they have not been asked, but we need them. We cannot be able to come to these second order derivatives without finding the first order derivatives. So what we will do first is to find the partial derivative dz dx, and then partial derivative dz dy. Then we can now take all this answer from those first derivatives. That is why the first one is dz dx. As I have said, when we do a partial derivative with respect to x, we consider y as a constant. So we just look at y as any number. So which means the first term, the derivative will be of x squared, which is 2x. Cos y is a number, we just write it as it is. Y squared is a number, we just write it as it is. Then the derivative of sine x is cos x. Then that is the first derivative with respect to x. First partial derivative with respect to x. Now the second partial derivative is with respect to y now. So we'll consider x as a constant in this derivative with respect to y. Y is our variable. So we will go to the derivatives now, and we'll find that the derivative of cos y is minus sine y. That is where we get this negative sign from. The x squared remains as it is. Cos changes into sine y, and we get this first term. The second term, sine x remains as sine x. The y squared is the one that we are differentiating with respect to. Then we get it as 2y. That's why the first order derivative with respect to y is minus x squared sine y plus 2y sine x. Now we need to go and now do the derivatives that we were asked. The first one is d squared z dx squared. And that will be the derivative of this first one with respect to x. So it will be d squared z over dx squared. So we will choose this one and derive it with respect to x. So which means in this case, everything that is y here is a constant. That is why the derivative of 2x is 2, because y remains exactly as it is. Then the derivative now of cos x, the derivative of cos x is minus sine x. That is where you get this negative from. Y squared remains y squared, and cos changes to sine of x. So this is the second order derivative, the first one that we were asked here. Then we come to the second one, which is this one. Now with this one, d squared z dx dy. Already we've got dz dx, which is this one. Now to get d squared z over dx dy, we are supposed to take this one, dz dx, and find its derivative with respect to y now. So that we have d squared z over dx dy. We go to this one, and now we derive this with respect to y. So x is the constant here now. So we go to y, and the derivative of cos y is minus sine y. That's where we get this negative from. This 2x remains fixed as it is because it's a constant, and therefore this one changed to that one. Then this derivative is the derivative with respect to y. So that's why we are going to take this one and derive it and fix this one as it is, cos x remains, and now this y squared is derivative is 2y cos of x. And finally, this one. So which means because now we are looking for the second order derivative of z with respect to y, we must go to dz dy and find its derivative with respect to y to get our dy squared at the bottom. And then we will get onto this one with respect to y. So this is the one that we derive. This is a constant. That's why you still see x squared as it is there as a constant. What is the derivative of sine y? It is cos y. Then we've got now the derivative of 2y, which will be 2. And then this sin x remains a constant, and that is your derivative of power 2z with respect to dy squared. So this derivative, in actual fact, is the same as d squared z dy here at the bottom. This one is exactly the same as d squared z dx dy. But this one is the same as d squared z dx here at the bottom. So you can go and on your own go and do d squared z dy dx and check if it is the same as this one. I think that you can do it on your own. So the next question, if you do not have any question in the previous one, will be this one. Now, as I have said in the previous slides, I always see this kind of a question in the exams. I mean, in the previous exams that I marked, I always see a question like this one. So let's just pray and hope that whoever the examiner, maybe they have brought it again. If they bring it again, the formula may not be this one. They may give you any other formula, but the way of doing this problem is the same, irrespective of the formula that is given there. You just need to understand when we go through these steps, what is it that you are supposed to do. Now let's first read the question together. It says, if theta equals k hl v to the power of minus half, where k is a constant. You know, this equation could have been given as khl all over square root of v. Then if it was given like that, you will need to first change it to look like what it is now here. So the examiner here was generous and gave you the equation in the form that you can just do whatever you have to do with it as it is. But if it was KHL all over square root of V, you were supposed to manipulate a little bit before you do any differentiation. Right, now it says K is a constant, so which means that K is a number. So there won't be any derivatives that involves the value K. K will just appear there as a constant. So because now it means H, L, and V are variables, then we may want to listen to this question going forward. It says, and there are possible errors. So there are possible errors of plus or minus 1% in measuring H, L, and V. So this say you are doing an experiment. And in that experiment, you are measuring values H, L, and V. Now, say you are measuring what? Say concentration of H in this KHLV to the power of minus 12 mixture. So I can find that the concentration is 7%. And one of you can find that it is 7.1%. Another person can find that the concentration is 7.3%. Another person may find that the concentration is 6.9%. Another one can find that the concentration is 6.8%. So can you see that all these values that I've just mentioned are very close to 7? but they've got a variety going down and going up. So that is what they mean by saying an error of plus or minus 1%. So it means that it can be the actual concentration can be, say, 15, but somebody can find that it is 15,7. Another person can find it's 14,9. Another person can find it's 14,6, and so on. So all these errors are between -1 and 1 of the original value. That is what it means by errors. So now we need to find, with this plus or minus 1% of errors on H, L, and V, we need to find the maximum possible error. So this word maximum is very important. It will be very important when we do our calculations, and you will see why I say it's very important. But now they may have said, find the minimum possible error. Then I will explain what we would have done if the question was, say, find the minimum possible error. So now let's concentrate on this word maximum possible error in the calculated value of theta. Value of theta is the main concept that we are measuring there, but it has got these three variables over there. Now, whenever you get a question like this one, you go to your information booklet or your information sheet, and you go and find there's a formula there of small changes. That formula of small changes is there in your information book, and it it needs partial derivatives of H, L, and V. That formula in there, it needs partial derivatives of H, L, and V. And it needs you to use this derivative together with the small change on H, small change on L, small change on V. And you will see the formula as we go on. But firstly, we will need partial derivatives of H, L, and V. So we'll come to this equation and find partial derivative of theta with respect to H, find partial derivative of theta with respect to L, partial derivative of theta with respect to V. Then we will take those and we will put all those together, and now we will be able to include these errors that we have in plus or minus 1% of each one of those three variables. Sometimes you may have only two variables. Then it means that it's only those two variables that you are supposed to derive and put together a formula that gives you the change in theta as or composed to the two variables that are given. Sometimes there can be four variables. Then it means that you will have small errors on four different things. Here we've got three, so we'll be adding three different errors. So firstly, we need partial derivatives. The first one is partial derivative of theta with respect to H. And if you look at this equation, H is power 1. So when you derive with respect to H, it will be 1 times K, which is K, H to the power of 1 minus 1, which is H to the power 0. That's why you don't see any H in this formula. L and V are going to be considered as constants. Remember, when you do partial derivatives, whatever derivative you are using there is the only derivative. The rest are constants. That's why you'll see all this remaining as they are. Then you do the second derivative with respect to L now. So it is partial derivative of theta with respect to L. And then the L is the one that is disappearing because it is L to the power 1. Multiply by K becomes K. And L to the power 1 minus 1, it will be L to the power 0. So you have got your K, H, V to the power of minus half. The rest of the other variables are considered as constants for this partial derivative. And finally, the derivative of theta with respect to V is minus half K to the power of HLV to the power of minus 3 over 2. Because when you do the derivative with respect to V, you will take the power of minus half, multiply it in front, and you get minus half K. H remains and L because they are constants. But with V, the power minus half must subtract 1 in the derivative. So what is minus half minus 1? It becomes minus 3 over 2. Then you have got your three partial derivatives. Now, that formula that I'm talking about is there in your information booklet. You go and check it, and it looks like this. So the change in the change in theta, which is used, we use this sign, is called delta. So delta theta, it means change in theta, will be determined by small change in h, which is determined by the partial derivative of h multiplied by the change in h itself. The same applies to the partial derivative of L with the change in L itself. The partial derivative of with respect to V multiplied by the change in V itself. Now, this is where we now do the substitutions. Now, the change in H, as we are told here, all of these H, L, and V are changing at the same rate, plus or minus 1%. So in place of change in H, we will put plus or minus 1%. Here, plus or minus 1%. Here, plus or minus 1%. All these ones are going to be replaced by their derivatives that you see on the left-hand side. And then that is what you get. Now, the first one is this derivative. If you can see, it is replacing this one. This derivative, it is that one over there. It replaces dh over dh. And then the change in h will be plus or minus 1% of h. Now, 1% of h is 1 over 100 of h. And 1 divided by 100 in decimal, it's 0.01, plus or minus. Right? Then we do the same with d theta dl. We replace d theta dl by its derivative, which is this one that is there. And then it is plus or minus the change in L, or the same percentage, 0.01. Then we've got the last derivative, which is minus half k HLV. And then you come and put it here. And then the change as well is plus or minus 0.01 V. Now, this is where I need you to listen very carefully. Remember here, we want the maximum possible error. Now, this is where the signs now come into play. For us to get a maximum change here in all these values, to get the biggest possible value, we can do that when this negative here is positive. How can this become positive? We can take this factor of minus 1 and remove it and remain with a positive sign and take it inside here, inside this bracket. When this negative sign gets inside this bracket, the negative that you see there becomes the positive that you see on top becomes a negative. The negative here at the bottom becomes a positive. So to get a maximum output from this expression here, we need a positive sign there. If it was minimum here, minimum possible, we would leave this negative as it is and leave the plus or minus as it is inside. But in this case, because we want a maximum possible, we don't want to reduce this number. We want the biggest possible number that we can ever have inside here. So that is why we will factor out this negative one, put it inside here. When we do that, this plus or minus will just swap around. You will find that the top sign will be negative, the bottom sign will be positive, but it will still be plus or minus 0.01. So that is why in the next step, you see what you see, which is that. So what happened here from this step, which is also very important to come to this step, is that the plus or minus is there for each and every one of these terms. There is plus or minus here, plus or minus there, minus or plus there, if you remember, but we can just put it the other way around. So we factor that out, which is what you see sitting there. Then K is there everywhere. From here, K is there, K is there, K is there. We factor it out. There it is. Then L is there here, but also L is here. You see here, there's no L, but here there is L. So that is the one that we have taken out to while you see there. Then the H as well. H, everywhere else there's L. Everywhere else there's H. Here it is not there, but inside this bracket, H is there. That is the one that we take out to sit here. And then also the V. Now with the V, we need to be very careful. What the V that we must take out from here, we must take out the V. We must take out the V here. That must resemble the original V there on top. which is v to the power of minus half. Now, if we can factor out here from this v to the power of minus 3 over 2, and we factor out v to the power of minus half. You remember when you do factoring out, what you do is when you have factored out this thing here, you go and say this, which you have, divided by that. So when you take the whole of that and you divide by this, you will see that k and k will cancel, h and h will cancel, l and l will cancel, v to the power minus half and v to the power minus half will cancel. And what is only left in this bracket is this 0.01 for the first term. For the second term, you do the same. You say this divide by the common factor that is outside. Then the plus or minus comes out, which is this one. Then the k will divide the k, the h divided the h, and the L, which is in here, divides this L, and the v to the power of minus half divided by this one, and then they are all gone, and you are left with this 0.01. Now, this is the one that is a little bit tricky. So you'll remember that this plus came when we said we want to maximize. Now, if it was said minimum here, we would have left this negative as it is here, because we want a smaller value. Then the minimum, if the question says minimum possible error, then we will have a minus sign here for this. So this one will remain positive, but this one will be a negative. So the result at the end will be the value smaller than what we will get in this question, because in this question we want maximum. Now, the trick that I was talking about is when we take out that common factor, KHLV to the power of minus half. What you can just maybe memorize here is that the common factor that you always take out here must be the original that you have there. I think if you can memorize it that way, it will make your life easier. Every time when you are at this step and you want to take out a common factor, it must be what you are given there on top, exactly as it is, which is this one. Now let's see how we get this 0.05. Remember the sign? I explained about the sign already, the plus sign. Now let's check how we get this 0.05 from that. So this is how it goes. So we are saying the whole of this divided by what we have outside. The plus or minus is out, which is this plus or minus, it is there. And then we say the whole of this divided by that, k and k cancels, as you can see. H and h cancels, as you can see. L and L cancels, as you can see. But now we have v to the power of minus 3 over 2 divided by v to the power of minus half. Let's see what we get. What we get will be v to the power of minus 3 over 2 minus half. It will become plus half. So then what is minus 3 over 2 plus half? It will be minus 2 over 2, which is
2 over 2, which is 1.
Come again. Somebody said something.
I was just saying it's 2 over 2, which is 1.
Which is 1, which is v, isn't it?
That's correct.
After when we divided, which is this v that is here, that is there. So if you can see this v here, if you can take this v and multiply it with this one, take this v power 1, multiply it with this one, the v that will be there will be power of minus 1. Actually, it will be minus 2 over 2. After we say this divide by that, it will be v to the power of minus 1. That v to the power of minus 1, if you multiply it with this v, then you get v to the power of 0, which is 1. Or else we can say, let's take the whole of this, divide by that. Then we will get v to the power of minus 1 here, and v to the power 1 here. V to the power of minus 1 times v is v to the power of 0. That is why the common factor that is outside, it must just always have to be that one all the time. Then this one will sort each other out, like v to the power of minus 1, which is our minus 2 over 2. We'll multiply with this v to the power 1, and you'll get v to the power of 0. Then that is where we're getting this now 0.05, because there is this half. This half now must multiply this 0.01. Now 0.01 multiplied by half or divided by 2. Then 2 will go 0 into 0, which is that one. 2 will go 0 into 0, which is that one. 2 will not go into 1. it will go 0, and you add a 0 at the end, and then you get that 5. So it becomes 0.05. You can even use your calculator and put 0.01 divided by 2. The answer will be this one. Now, this is the only part that I thought I need to spend time so that you don't get confused. So if the question was minimum possible here, we would have left this negative. So it will be minus this value. So because we're looking for a maximum, we factor out the -1, put it inside here, and it changes these signs. There will be minus plus. That's the only trick that is in here. Then from there, as you can see, the whole of this that is there is your theta that we are looking for. So you can come and replace KHLV to the power of -12 by theta on the left side, on here. And you can add this. These are just numbers. So 0.01 plus 0.01 is 0.02. Plus 0.005, it will be 0.025. So what we have here is that the maximum possible error will be plus or minus of theta. On theta, it will be plus or minus 0.025 if each one of these variable has got an error of 1%. Now we may want to get this answer 0.025 in percentages, because here they give us the errors in percentage. Now you just have to check what is 0.05 in percentage. Now, in fact, first you can change this into a fraction, and it will be 25 over 1,000. Now, what is 25 over 1,000 in percentage? So you multiply by 100, and you will eventually get that the percentage is actually 2.5. So the maximum error, sorry about that, the maximum error on this theta will be 2.5%. So if it was minimum, if the question said minimum, we would have subtracted this 0.05 from 0.02, and it will give you whatever decimal that is there, and that decimal will be smaller than this one. So that will be the minimum error. And we are done with this question. As I've said, I've seen this kind of a question almost everywhere, all the time. So this, if this the examiners are still in the same thought of mind this year, they should include something like this. If they do, as I have said, it can be having 2 variables only. It can have 4 variables, as long as the formula must be consistent. If it is 2 variables, so it means this one, if V was not involved here, it means our variable will be H and L. So we will have only these 2. If there are 3, like we have, these 3. If it's 4 variables, we will say plus. The other variable is partial derivative, and then the delta of that variable, and so on. There can be 5. There can be whatever number. It doesn't matter. The way of doing it is exactly this one. No question? Now let's go to Maclaurin series. Also, this kind of a question is always there as well, unless this time they don't want to give you this question, but it is also the application. This question is also the application of differentiation, as you will see. So the Maclaurin series, a series, if you can remember mathematics high school, when you were still doing sequence and series. A sequence is a sequence of numbers with a pattern, and a series is the sum of those individual terms. So a Maclaurin series will be a sum of terms of a sequence. It was named with this name because this guy is the guy who found this kind of a series. So how does it go? You will be given a function of x. Like in this case, our function of x says it is x multiplied by e to the power of x. Now we want you to rewrite this x as a series, as a sum of terms of parts that will add up to be able to give you back the function f of x. And the process is very simple. Then sometimes the examiner can tell you up to which term you must stop expanding. But in sequence and series, if you can do 3, 4 terms, it's enough. If nobody says anything, you can just do 4 terms, the first 4 terms. But somebody can say, give 5 terms of the expansion, or give 6 terms of the expansion. Then you're supposed to be able to continue with this. So in my case, I just did, I did 4 terms here. But we will be able to explain to you how we can do this 5th term, how we can do the 6th term, and so on. So the secret here is on the function f of x equals to e to the power of x. So that is your function f of x. You just copy it down as it is. Now you just need to take this function and continuously find its derivative. You do the first derivative. So, but now, because this function of x has got x multiplying e to the power of x, so it's a product of two functions of x. So we still need to use rules of differentiation. When you've got a function of two terms that are multiplying, and then it means that you're supposed to use the product rule. So the product rule here for the first derivative will give us a derivative like that. How does this derivative come about? So when you want to find this derivative using product rule, you will find the derivative of the first one and fix the other one. So the derivative of x is 1, so it will be 1 multiplied by this one fixed, and it is there fixed. Then you fix the other one, which is this x, and you find the derivative of e to the power of x. Now the derivative of e to the power of x is e to the power of x. Then you have the expansion, the first derivative as that one. Now you need to continue doing the derivatives. I said I've done. I will do until I think the fourth term. The fourth term will be the derivative 3 times. Then there can be the derivative 4 times, the derivative 5 times, 6 times. It can go on indefinitely. So the second order derivative now is the derivative of this one. Now because now we have got this term which looks like f of x. So we know that the derivative of, when you come to this part, the derivative will be this one. So now we are going to say the derivative here of this derivative will be this derivative, which is e to the power of x as it is. First, put it aside. Then the derivative of this will be the whole of that. So which means that the second order derivative will just be 2 of this plus this one as it is. Then the third derivative, you know that the derivative of this one will be itself as it is 2e to the power of x. Then the derivative of this one will be the whole of that. So which means that the derivative, the third order derivative, will now be 3e to the power of x plus x e to the power of x. You can see that you can do power of 4. So you can have f. Now, when in your textbook, when they write the fourth derivative, they use Roman numerals. So it will be f iv there on top for the fourth derivative of that. So it will be 4e to the power of x plus x e to the power of x. If you go to the fifth derivatives, it will be f with a v there representing 5 in Roman numerals of x. Then it will be 5 e to the power of x plus x e to the power of x. So you can go on and on with these derivatives, but I will stop here with this one. Then now, what do we do next? Now we need to substitute the 0 for each and every x from the original equation for f of x up until the last one that we have there. Then to get f of 0, it will be 0. The 0 is coming about here because when you put x is equals to 0 here, you get 0. 0 multiplied by any number, the answer is 0. You get that. So it means the first term of this series, because the terms of this series will have coefficients that we are calculating here. Here in this part, we are calculating coefficients of this Maclaurin series. So the first term, its coefficient is 0. So it means that the first term will not exist in our series. Let's see what happens with the second term. We put 0 here for x. Then we put 0 there. We get e to the power 0, which is 1. Then we put 0 here, it takes away everything. So all these terms will go. Only these terms will remain, because when this x becomes 0, all these things are falling away. So which means that the first derivative, its first coefficient will be 1. Second one, its second coefficient will be 2. Third one, its third coefficient will be 3. So the fourth one, the coefficient will be 4. The fifth one, the coefficient will be 5. The sixth one, the coefficient will be 7. If we can ask the nth one, the coefficient will be n. So that's how these things work. So these are coefficients. Now, how does the series work? The series work in a formula like this. All the time, the formula is the same. It's like that. So it is f of 0, which is not always 0. Sometimes you will find that when you do your derivative, you will find that you get a certain number. So which means that it is going to come and sit here in place of f0. So, but in our case now, we will not have that because it is a 0 itself. Then the second coefficient is the first derivative, which is 1. So here we'll be replacing this with 1. X now is coming for the first time. So it is x to the power of 1. So in actual fact, it is supposed to be divided by 1 factorial. This was supposed to, in fact, be f of 0 divided by 0 factorial. And I hope you all know that 0 factorial is 1. So this one is this one over 0 factorial. This one is the first derivative, x to the power 1 over 1 factorial. And the second one, the third term is the second order derivative, which will, the coefficient will sit here, and you will have always your x squared over 2 factorial plus third order derivative is x cubed over 3 factorial. So as I said, you can go on and on. The next one, which is f of power, the fourth order derivative, it will be x to the power 4 over 4 factorial. The next one will be x to the power 5 over 5 factorial, and so on. So you can be able to continue on your own. Depending on the examiner, if they don't say anything, you can stop with 4 terms. If they tell you, go to the 5th term, for example, these are 1, 2, 3, 4 terms, then you will add the 5th one. If they say, go to the 7th term, you will have this first term, second term, third term, fourth term. 5th term, it will be the coefficient that you will have calculated. And in this case, we know it will be, if it is 3 factorial, it will be here 5 x to the power 5 over 5. The next one will be 4, actually, x to the power 4 over 4 factorial. And the one after that, 5, x to the power 5 over 5 factorial. The next one after that, 6, x to the power 6 over 6 factorial. And it goes on like that, according to the sequence that we are seeing there. But if it is another function of x, these values will be different. The things that will be the same is the formula. The formula is the same. The numbers that are sitting here, they depend on what you have calculated up there. Then here, it's just a matter of substitution. Then it is starting with this one, because here you will have put a 0. This one is gone. Now in the next one, which is f prime at 0, it's 1, as you can see. There's a mistake here, because here it's x to the power 1. So here, this one is not supposed to be there. This is my mistake. Now, if you can see, this one is not supposed to be there, because the f of 0 is 0. So this is a 0 here. Please note that this is 0. Because now the next term is the one where the coefficient is 1. You put 1 there, and then x is appearing for the first time, power 1, which is this x. So this here is not there. It's supposed to be a 0. So the first term should be this one, because there it's a 0. So I'm so sorry about that. So this part here, it's a 0. Then this term is from this one, x power 1, coefficient 1, that is the one. Then the next one is the second order derivative at 0, which is coefficient 2, which is that one, and multiplied by x squared over 2 factorial. So 2 factorial, as you know, is 2 times 1, which is 2. So 2 and 2 should cancel, and then this term should be x squared. Then the next one, 3 factorial, it's actually 3 multiplied by 2 multiplied by 1. 3 multiplied by 2 multiplied by 1. That is 3 factorial. So 3 into 6 goes 2. So the next term here should be x to the power 3 over 2. Then if you want the other terms, you can do them in the same way. So which means the final answer has got a 0 here. This value is not there. So it starts from here. So the Maclaurin series for x e to the power of x is x plus x squared plus x to the power 3 over 2 plus the other terms as you go, depending on the number of terms that are required. And that is how to do a Maclaurin series. And I think we are done with the application of differentiation. Now, I want us to do this few integrations. So what happened was that ma'am asked me to do maybe, I think, 3 questions on integration. I think I have done much more. So I will move a little bit fast so that we can finish by 8. But please do not allow me to continue if you do not understand. Stop me. And I want to show you how easy these things are. Integration, as I have shown you with differentiation, this is very, very easy, because you guys have got the formulas with you in the examination. So what I'm just going to show you here is how to copy from that information booklet, and you get all those answers correct. It will not be a very difficult thing to do. Now I am starting with these two rules first, so that I can be able to explain, and we are going to be using all these rules throughout this presentation today. The rules of integration is rule number 2 and rule number 3. Now, if you go and check in your in that information book, rule number 2 goes like this. It says if you've got a function of x, and that function of x is raised to the power of n, and then there is a derivative of the function of x accompanying that f of x raised to the power of n. The reason why I've put this in red is because this thing in red, it must just sit there to facilitate the process of integration on this f of x. It does not do anything, but it must be there. And as you can see on the right hand side, it disappears. It is not there anymore. What happens is now that this f of x now behave like an x. So this derivative sits here to just make a function of x that sits there to behave like an x. How do you derive x to the power of n? X to the power of n is derived as you take n, you add 1, and you divide by the result plus c, and you are done. So that is what you need to put in your mind from now going forward, because there will be a lot of these red things that we will need to be there for us to be able to do this kind of process. Now, it is specifically said here for n equals not equal to minus 1. Now, let's see what happens if we can allow n to be equal to minus 1. You will put minus 1 there in place of n. Minus 1 plus 1 is 0 there. And it will be dividing by the same result, which is minus 1 plus 1, which is 0. And this will be undefined. So when n is equals to minus 1, this does not work. Only when n is equals to minus 1. But all other negative powers, it is minus 2, n is minus half, or whatever, you use this one. When n is minus 1, then this is what happens. Your f of x will be like that. If you rewrite this one, if you take it up, like to write it like this one, it will be f of x inside the bracket, power will be minus 1 for this one. Then the derivative must be there as well. Then this derivative must just sit there to allow this one to become ln of f of x. Now, if you remember, this process called integration is just the reverse process of differentiation. Now, if you can take the right-hand side and differentiate it now, you should get what is inside this side. Because the derivative of this is that power, multiply it in front, it cancels with this one, and from this power, subtract 1. Then it will be this, multiply it in front, from this power, subtract 1. And at the end, multiply by the derivative of what is inside. And you get all that you see over there. Same applies to this one. Find the derivative of ln of f of x is the derivative of what is inside, which is that one in red, divided by the f of x itself, which is this f of x. So this is exactly just the reverse process. But when you are going from left to right, this derivative, it has to be there. And then this can do that. It has just to be there so that this can do that. So even when we deal with trigonometric functions or whatever other things, we will still be using this rule throughout these explanations. You must just remember this rule. It's very, very important. They didn't call it the general power rule of integration for nothing. It's very powerful. So let's start. Say we've got that cos power of 5 cos x power 5. Now, what does this mean first? This means we want the integral of cos x multiplied by cos x multiplied by cos x 5 times. This is the same as cos of x all in brackets to the power 5. Now you will go throughout the integrals that you have in your information booklet there. You will not find an integral of cos power of 5. So what you will find there, you will find the integral of the previous integral that I just shown you. Now you need to, on your own, from what you are given, be able to create that power rule that we had there. Now you see the power of 5 is odd. If this power was even, you could do that by applying squared identities. But here you cannot, as it stands, because the power is 5. So, but you can create an opportunity for yourself to use squared identities, even in this case, by taking this cos x power of 5 and split it into one power that is even and another power that is power 1. And this will look like that. That cos power of 4, also you can rewrite it as cos squared x power 2. If you, this means it's cos squared x multiplied by cos squared x, which is cos to the power of 4x times this cos x brings you back to exactly your cos to the power of 5. So from here, if you can understand that these two steps are exactly the same, then we can now continue. Now, I said we are doing this so that we can be able to use squared identities. And now you remember that if you go to your trigonometry, in your information booklet, you have got those trigonometric identities, they are there. So you go there and check. What is an identity that contains cos squared? You will realize that it is this one. So you can replace cos squared by 1 minus sine squared. This power of 2, well, that was outside, it is still there. The cos x dx, just leave it like that for now. Then we go on. Then we are supposed to now multiply out here. So this is multiplying itself twice. And there are people who do the following. There are people who come here and say 1 squared minus this squared, thinking that you can do that. You can't do that with a negative sign. This is a binomial. So it's 1 minus sine squared x times 1 minus sine squared x. And you multiply it like you multiply binomials. So this answer must have 3 times, which is this one. So 1 times 1 will be 1. 1 times minus sine squared x is minus sine squared x. Sine squared x times 1 minus sine squared x times 1 is minus sine squared x. That is why you see a 2 there. So it is 2 of those sine squared x. Then sine squared x multiplying by itself, you get sine to the power of 4x. Now you've got 3 terms. All these 3 terms have got a friend here, and the friend is cos x dx. And one other thing, before we continue, I didn't mention this, I must emphasize this one. Now, this sign of integral has got no meaning without this dx. This dx tells us the variable with which we are doing integration, and it has to be there all the time. Because if I can replace this dx by, say, dy now, it means now this cos to the power of 5x is a constant now. So you can take it outside the integral and just have your integral with respect to y. So this has to be there. So that is why in the next step, you will see that this cos x dx will go to 1. Same cos x dx will go to this. Same cos x dx will go to that. And you get 3 separate integrals. Now, the first integral is just 1 times cos x dx, which is this part. And this one, you just go straight to your integration table there in your information book. You will find the answer to this one. Straightforward. You don't even have to think here. Now, let's talk about the other 2. Now, when you multiply this one with cos x dx, you actually get minus 2 sine squared x cos x dx. So what I did was just to take out the minus 2, take it outside the integral sign, because minus 2 is a constant. You can be able to take the constant, you can put it inside, or you can put it outside, you are allowed. What you cannot do is to take out something that contains x. You can't do that because you are deriving with respect to x. So after taking out the minus 2, which is this one, you are left with the sine squared, which is this one, and your cos x dx comes here and multiply this sine squared. The reason I'm putting it in red now, it is because it is that general power rule now that is going to come into play. Because I always mention this, for you to be able to do integration, you must be very sharp with your differentiation. So if you are sharp with your differentiation, you will know that the derivative of sine x is cos x. So by virtue of this derivative sitting here, then this is your f of x, your sine x is your f of x raised to the power n, which is 2. So that general power rule applies with this one. The same applies to the last term, which is this one. It multiplies those. I've written this in red so that you can remember that this is just the derivative of sine x. So it makes sine x behave like x. That is why rule number 7 is the rule that that will apply for this one. It's rule number 7. Rule number 2, which I just explained in the previous slide, applies for these other two terms, which is the general power rule. And then this is how you get this answer. You can see how easy these things are, as long as you know what you're doing. Number 1, importantly, you must create an opportunity for the general power rule. The general power rule says whatever is f of x must be accompanied by its derivative. And you made this happen here when you split this and have cos x. Then you just leave this one everywhere as it is until everything else that is there is written in terms of sign. Then everything else will look like this. Cos x is the derivative, cos x is the derivative. So this one behaved like f of x, how it behaved in the original number 2. If for some reason we had a power of -1 here, that is now when rule number 3 will apply. We will have ln, but we don't have any ln because we don't have any power of -1. Here is power of 2. That is why it is 2 plus 1, which is 3, divided by the result. This 2 is this one. The negative sign is this one. This 3 is coming from the integration of that. Then this one, the same applies. It is 4 plus 1 divided by the result. And that is where we get this 1 over 5, sine power of 5x plus c. These are dropped because it's the same as I've explained in the previous explanation. Now, if you want to check whether this is correct or not, you can find the derivative of this thing. You will see that the derivative of this sine x is cos x, which is that one. The derivative of this, the derivative of this is you take this 3, multiply it in front, you will get a -2. And then from the exponent, you subtract 1, you get sine squared. But then you must also multiply by the derivative of sine x. What is the derivative of sine x? It's cos x, which is that one. So the derivative of this is exactly that which you have there. Same applies to that one. So we are done with this question. That's how you should attack anything that has got an odd power. As I have said, if the power was even, we would just rewrite everything, put the power outside, and put if it is cos, a cos squared inside, and you square that. You use the squared identities, replace cos squared with that, and you square that until you use your trigonometric identities for compound rules to remove the powers and so on. So we are moving to the next question. As I said, I will move a little bit fast so that we can catch the time, but don't allow me to move if you do not understand. Viva, we have just got the example which has got a power that is even. Now let's see how we attack this one. As I have said, here you cannot split a sine of x. If you split one sine of x here, you will have a power of 3 sine cubed x multiplied by sine x. It won't work here because the power is even. So what we do, we rewrite this as a power of 2 inside and a square outside. But what is in here, we can replace it using squared identities. The sine squared x can be replaced by squared. If you go to trigonometric identities, you will realize that sine squared a is equals to half into 1 minus cos of 2a. The reason why we are doing this, we want to do away with these powers because all the integrals, if you can check them in your information book, we don't have integrals that are inside here with powers. They are names of trigonometric functions as they are. So we want to try and do away with the powers. And now this is the trigonometric identity that help us to do away with the power that is inside here. So we will go to this identity, replace sine squared a with that. So in this case, it's sine squared x. So we are going to replace sine squared x with half into 1 minus cos 2a. This identity is there. You can check your information booklet. It's there. Then you come and replace in here, and you get that. But remember, there's this power of 2 outside, which is that one. So which means you are still having to square this one. When you square 1 over 2, you will get 1 over 4. And it is just a number, so you can put it outside the integral after you square this thing. Then you square this. When you square this, you will have this. This multiplied by itself, this multiplied by this multiplied by that, and this multiplied by itself. And you will eventually get something like that. 1 over 4 We have taken it outside because it is just a constant, but we don't throw it away. We keep it there. Then the 1 is from the 1 times 1, and the 2 cos 2x is from this times that, and this one is from this multiplied by itself, which is that one. So we still have got a problem here because we've got this power of 2. There's no integral with power of 2. So we apply the same, we go to the same place where we found this integral. So this identity, and we find the other identity for cos squared, which looks like that. Then we replace this with that identity in place of cos squared 2x. So now that our a here is 2x, then it means that our cos 2a will be twice this one. So we will have now, when you go to the next step, you will now see a 4x. It's coming from this identity. Then we do that. So what I just did was to separate all this so that we've got 3 different integrals. The first one will be the 1 for 1, which will be 1 over 4, 1 dx, which is this one. 1 dx is this one. Then the second one is this one, which is 2. Is there anyone who wants to say something?
Yes, I want to ask something. Okay.
Yes.
On that step there, 1 over 4, that step, I wanted to
Yes.
ask, did you actually multiply that square that's to the power of 2 by 1 over 2 to get 1 over 4, and then you
Yes.
just put everything the same, and then you also multiply this square by negative cos 2x, right? And then you got positive
No. No, we didn't do that. That we didn't do.
Okay.
That we did not do. This is what we did. We have applied, because look, this half is multiplying this bracket, isn't it?
Yes.
So if you have got a multiplied by b in brackets squared, then you get something like a squared plus b times b squared, right?
Yes.
Which is what we applied on half and this bracket, but we have not entered the bracket yet. So this half squared is this 1 over 4. Now this one, 1 minus cos 2x squared, you don't take the power of 2 and put it inside. You can't do that because of the minus sign. So what you do is you have got 1 minus cos 2x multiplied by 1 minus 2 cos 2x. We are multiplying 2 binomials. So the 1, this one, will multiply 1 minus cos 2x. And then this cos 2x will also multiply 1 minus cos 2x. And when that happens, when 1 multiplies 1, we get this one. When 1 multiplies cos 2x, we get minus cos 2x. When cos 2x minus cos 2x multiply 1, we get another minus cos 2x. When we add them, because they are like terms, they give us this one.
Okay.
Then now we say cos 2x minus cos 2x times minus cos 2x, and it gives us this one, cos squared 2x.
Okay. So, okay. Now I do understand. You have used binomial factorization, like binomial or whatever you call it, just to get this
Binomial
expression.
multiplication.
Okay.
If you know binomial theorem, then you can even apply binomial expansion, the binomial theorem. You will get the same result.
Okay.
What you
Thank
must never do, which is, I like that question of yours, because there are people who will come here and they will say the following: the square here on half is 1 over 4, the square here on 1 is 1, and the square here on minus cos 2x is this one. This will not be there. Then everything now from there is wrong. You can't do that.
Okay. Noted. Thank you.
Perfect. Thank you so much for the question. Now, now we just put individual terms here. It's with its own integral. The first one is this one. Then the 1 over 4 applies for every one of these integrals inside. That is why you always see 1 over 4 outside. Then it is a negative sign that comes out of this negative that was there. So that is why we've got a minus 1 over 4 outside. This 2 cos 2x, I have put it there as well. Then here you've got 1 over 4. Now, the whole of cos squared 2x is replaced by the identity that we have here. As I have said, because here it's a and here is 2a, here is 2x, then that is why here we've got a 4x, because it must be double this angle that is there. That's where this 4x is coming from. Now, this half is the one on the identity itself. So everything that is in here is from this identity. But then we also have a 1 here. So this one, when we apply the dx inside, it will be now this half times 1 over 4, which is 1 over 8, 1 dx. It has got a friend, which is this one. So we can just put them together and add 1 over 4 and 1 over 8. Then this one will remain as it is. And here we will have now our integral. We will have 1 over 4 integral of cos 4x dx. And we get now to use rule number 7. So now let me explain. And I want to explain the red numbers there. If you go and check rule number 7, rule number 7 is the integral of a cos function. It looks like this. It says, is the integral of, here there's f prime x, which is the derivative of what is in here. Cos of f of x dx. That's how it goes on the left side of that rule number 7. If you check. So which means for us to do an integral of cos f of x, we need the derivative of x to sit there. Luckily in this one, the 2 was already there. We didn't invent this 2. It was there. I just changed its color here so that you know that this is a derivative that's supposed to sit there to facilitate the integration process to happen. And when we go to the next step, it will not be there. It will disappear. So now when we come to this 3 over 8, this 3 over 8, if you remember, I said 1 over 4 times 1 over 2 is 1 over 8. 1 over 8 times 1 dx. We are adding it together with this one because they are similar terms. So 1 over 4 plus 1 over 8. If you can add them, they should give you something like this. Unless my arithmetic has done a number whatever on me, a number on me here. But you can check if this is correct. But if it's not correct, you can just replace this with the correct number. But I think it's correct because 1 over 4 is the same as 2 over 8 plus 1 over 8 is 3 over 8. So this one, 3 over 8, is coming from this and that. Right? So we are done with this part. That is the first integral. The second one is this one as it is. We just copy it down as it is, but this is sitting there as a derivative of what is sitting inside there. Now with this one, the cos 4x dx had a 1 over 8 outside. Remember, this 1 over 4 will multiply this and that together. And you have got a 1 over 8 outside. But for us to do this integration, we need a 4 to be there, which is a derivative of what is in here. Now this 4, because it's required, we put it in here and multiply the 1 over 8 by a 1 over 4. That 1 over 8 times 1 over 4 gives us this 1 over 32. And if you can take this 4 outside, now it will be 4 over 32. 4 over 32 is the same as 1 over 8, which is that one. So here, we didn't change anything. We just put a 4 inside that we need and multiply outside by 1 over 4. So 1 over 4 times 4 is 1. This 4, we need it to sit here to satisfy rule number 7. Check rule number 7 on the left side. You will see it looks like that. Then you apply it and you get those answers. So the answer comes like this. Here, 1 dx, because we are using the variable x. 1 is the same as x to the power 0. X to the power 0 plus 1 is x to the power 1. Divide by 1 is x over 1, which is x. 3 over 8 is the one that was there. That is where we get this 3 over 8x. Now, this one minus 1 over 4 is there. Rule number 7, you take it straight there. It gives you that the integral of f of f prime x cos f of x is sine of f of x, which is that sine 2x that you see there. Same applies here because this is the derivative of that. Then the integral of cos is sine 4x. Done. And that's the answer. Next question. Now we've got a mess here. We've got a mix-up of sine and cos, and we've got powers. Or one is power 3 and another one is power 2. If you remember the first question with power 5, I split the power 5. The reason was that I want to have even powers. You know, with even powers, there are a lot of other things that we can do with even powers. We always want to have even powers. So even now, we need even powers. This one is not even. So we split this one so that we can have an even power. And when we do that, we will be remaining with sine squared x cos squared x was there, it is there as it is. That sin x that we removed is here, there it is, dx. So this we will keep, and we will do other things that we have to do with these other two. Now, this is where your knowledge of differentiation come into play. You know that sin x, which is this thing that is here, is the derivative of cos x. So now it gives you an idea of what you have to do with these two. It means that you must all try by all means to have only cosine here, because you know that its derivative is sin x and it's already there. So what you do, you replace, or you replace this one, go to identities and replace this one with its equivalent, which is 1 minus cos squared. Now you've got your cos squared and the cos squared here. So when you take all these three things and multiply them inside the bracket, you get that. So for the first part, which is this one, I will explain the signs. So initially, you will have this cos squared x times sin x dx multiplied by 1. And it will be cos squared x sin x dx. Now, again, your knowledge of derivatives, very, very important. Now, the question is, what is the derivative of cos x? You will know that the derivative of cos x is minus sin x. That's why we need that derivative to sit here. So I have introduced that negative sign and countered it with a minus 1 outside there. That is where this negative is coming from. So if you take this negative, multiply it inside, you get exactly back 1 times all those that are there. So this has been done so that this becomes the derivative of cos x, so that we can be able to apply that power rule that I've talked about in the beginning. So the second one, we have got the minus already. It is there. So we just take it inside so that it can sit with sin x, because the derivative of cos x is minus sin x. So when we remove this negative from here inside, then this sign becomes positive. So we factor out the minus 1 and we take it inside, which is this minus that you see there. If you take it out, it can come and sit here, and then you will get back exactly your this times that sin x dx, which is that one. Now that we've got our derivatives sitting here, our cos x here with the exponents, derivatives sitting here, cos x with an exponent, the normal derivative rule number 2 comes into play. That's why the answers are, yeah, there's rule number 2 that you need. And here you add 1 divided by the result. That is where you're getting 1 over 3 from. Cos 3x. With this one plus 1 divided by the result, 1 over 5. Cos 5x plus c, done. That's how easy these things are. So the next question is about involve tan and sec. Now, also here, it needs you to know your derivatives. And if you know your derivatives, then you can be able to play around with these values that you have there. So if you go to your derivatives, your derivative of tan x, derivative of tan x is sec x tan x. That is the derivative of tan x. The derivative of sec x is sec x. The derivative, sorry. Pardon me. The derivative of tan x is sec squared x. Sorry about that. The derivative of tan x, if you go to the table of integrals there, it is sec squared x. And the derivative of sec x is sec x tan x. Now, it is either one of those two that you need to isolate. So let's see if we want to use the derivative of sec x. Because if we want to do that, we must reserve tan x sec x aside as a derivative of sec x. So if we try and take away 1 sec x here and 1 tan x here, we're going to remain with tan with power 5 and sec with power 3. And there is nothing we can do with those. So which means that it cannot be the derivative of sec x that we're looking for. It could be maybe the derivative of tan x. And that is possible here because if we can rewrite this sec to the power of 4x as sec squared x times sec squared x, we will have preserved the derivative of tan x. And that's what we are going to do, because of the fact that the derivative of tan x is sec squared x. Then we are going to do that. So we split the power of 4. The information of which one to split and which one to reserve and whatever, it has come from your knowledge of derivatives. If you didn't know this, then you will not know what to do. So you should know this, and you should also know the derivative of a sec function, which is tan x sec. It is so if these powers were odd, say if this powers was tan 5 here and sec 3 there, then it means that we would need the derivative of sec x here. You will see that the derivative of sec x will be sec x times x. Then you will split them, both of them. You peel away tan x, you peel away sec x, and you reserve them to be the derivatives. But here we need this one. So the tan must be preserved. So sec squared is sitting here as the derivative of tan x. So now you go to identities, and you want to replace this with something that contains tan. And the identity is this one. It is there in your identities. So you replace sec squared by 1 plus tan squared. In place of this, you are going to write that. This one you are going to leave because it must sit there as a derivative of tan x. That is why we replace this one only. Then we get that. Now from there, this derivative of tan x will multiply this one together with this tan to the power of 6x, and we will have one integral. Then this derivative of tan x will multiply this one together with that tan to the power of 6x. Sorry. And we'll get another integral. That is why we see now two integrals. Now the first integral is for tan to the power of 6. You can see tan to the power of 6 times 1 remain tan to the power of 6. And now I've written this sec squared x in red because it is just sitting there, so that tan is our f of x raised to the power of 6 can do the general power rule, that first rule that we talked about. You can see that that general rule is used almost everywhere. So you need to master that. Now, when we multiply this tan squared x and this tan to the power of 6x, we get tan to the power of 8x, and the derivative is preserved. There it is in red. From there, normal general rule. You add 1 to the power 6, you get 7, divided by the result. 1 to 8, you get 9, divided by the result, plus c, and you're done. Ah, there we go. Now we've got odd powers, which I just mentioned now. All the powers are odd. And now we are doing it with respect to theta. So, with odd powers, what I'm explaining here also works in the same way if you are having cot and cosec, because the rules are almost similar. So what I'm explaining here, do use the same analogy when you deal with cot and cosec, because there are identities which connect the two. Now here, now we always work with squares. Now for us to create powers that are even, we're supposed to peel away 1 tan from tan cubed. We must peel away 1 sec from sec power of 5, so that we get something, because we know that the derivative of sec theta is tan theta sec theta. When we peel away those two values, we will preserve them as the derivative of sec theta. So this is what is left. In tan, we are left with tan squared now here. Sec, to remove 1 sec, we are left with 4 of them here. So that tan theta is here. Sec. So these two are our derivative of sec theta. What does that tell you? It tells you that now you're supposed to remove the tan squared. And there's an identity like that allow you to do that. So you replace tan squared with sec squared theta minus 1. You will find this in your information booklet on trigonometric identities. Then you replace tan squared there. Then from there, you do what we did in the previous example. This tan theta sec theta is a derivative. So it will go with this sec to the power of 4 multiplying that, and this sec to the power of 4 multiplying 1. And that is where you get this from. This power of 6 comes from power 2 times power 4. This one, power 6. This is the derivative, sits there. This one, power 4, as it is, the minus sign is this one. Sec power 4 is there. This is the derivative. Then that is the general rule. because you know that the derivative of sec theta is tan theta sec theta. So then rule number 2, that power rule, there it is. So 6 plus 1 divided by the result, 4 plus 1 divided by the result. And now let's quickly move to hyperbolic functions. Sorry. So hyperbolic functions have got their own identities. They work more or less the same as identities on trig, but there's some difference here and there. And they're all given to you in the information booklet. And also here, you need to know your derivatives. Now you know that in hyperbolic function, the derivative of sin of 3x should have something to do with cos x. And then you've got a 5 plus sin here at the bottom, which means that you go to rule number 3. Rule number 3 will tell you that when you've got an f of x underneath, and if you can have its derivative sitting there on top, then the answer will be ln of the one at the bottom. And you make that happen. You take that 5 plus sin 3x, this one, power minus 1. That is that restriction that was there, if you remember, when we were doing the general power rule, that when n is minus 1, it becomes ln of that. Now, if you go to your derivatives now, you will find that the derivative of sin 3x will be 3 cos 3x. Cos 3x was there. Cos 3x was there on top. It just needed a 3 so that we can have a complete derivative sitting here of that thing that is inside the bracket. So that is why we must bring a 3 and we counter it by putting a 1 over 3 outside. If you can take this 1 over 3 inside and multiply it here, it gives you back exactly what you have there on top. So this 3 is coming as a derivative of that 3x, so that it can be a complete derivative of what is in here. Now that we have achieved that, then the answer is the 1 over 3 is coming down here. This falls away now because it's just sitting there as a derivative of that. And we apply rule number 3, ln of what is in there, which is that one. And we are done. Another integral is now the integral of e to the power of 2x. Cos e to the power of 2x. Now, if you look at the integral, if you look at your derivatives, the derivative of e to the power of 2x is 2e to the power of 2x. So for us to go straight to the integral of cos, we need the derivative of e to the power of 2x sitting here. And already we've got e to the power of 2x there for us, which is part of the derivative of what is in here. It just misses a 2. So we put a 2 there and counter it with a half outside. So now the whole of that thing that is here in red is the derivative of what is in here. Then we go to the rules there. Go see rule number 19. It will give you the integral of cos. It's there in your booklet. You just copy the right-hand side. The right-hand side, it says it's ln sin of e to the power of x. This must be there as the derivative of what is in there. And you get that. And you're done. Now that power of 2 again. There's no integral with power of 2, even in the hyperbolic functions. But there are trig identities, there are hyperbolic identities that will help you to sort this power of 2 outside. And that is the identity that I'm talking about. It goes like this. It says sin squared x is a half into cos 2x minus 1. So we just replace sin squared x by what is on the right side, so that our integral becomes that. So we'll have 2 integrals now. One with cos, another one with only the 1. So we'll go to rule number 17 here for us to find the integral of cos of a function of x. But our function of x is 2x. So we need the derivative of 2x to sit with cos. What is the derivative of 2x? It's 2. Now, because we are bringing in a 2 from to compensate our derivative, so we must counter that by another half. This half is the one that we were having before. The other half that is multiplying to give us 1 over 4 is the one that is compensating for this 2. Because if you take this 1 over 2, multiply it inside, you get that half. You get this half perfectly. But we need these 2 to sit here. That's why we must bring another 1/2 and multiply it with this 1/2 to get the 1/4. Then now this is rule 17, exactly as it is. And then now we will have this half multiplied by -1 with dx, which give us this integral of x to the power 0 dx. Then we apply rule number 17 for the left side, and we apply the normal integration for the right side, and we get this as the answer. Our time is almost up, and so do you want us to stop here because it's 8 o'clock, or do you want us to finish the remaining integrals? I need your cue there. I don't want to stress you because 2 hours already is even a very long time. Should we finish the remaining integrals, or should we let me see how many are let me see how many are left. We're left with 3 slides, so which means we're left with 3 questions.
I'm suggesting we stop, sir. Some of us are writing tomorrow, so we have to prepare for writing also. We are writing a major tomorrow.
Oh, absolutely fantastic. Then if that is the case, then let's stop, and then the remaining solutions
Can
are
I,
done
can I
in this.
ask, can,
Yes.
can I ask you something, Munir?
Is it about this presentation?
Yes, if we can stop here, then
Yes.
are we gonna get another opportunity to finish the remaining?
No, we are not going to get any opportunity to do the remaining slides. The remaining slides, there are 3 slides, which I have done. The solutions are there. So ma'am will send you these slides. If you have got any queries on the solutions that are there, you can contact me and I can explain it to you individually.
Okay, no problems there. Then we can stop there.
Yes. So we'll stop here, and then ma'am will download both the lesson that we did on Monday and this lesson and upload it for you on Moodle. So you can access this presentation again, and then it will have this presentation. It will be there, and then she can email it to you actually, so that you can have the other 3 slides because the presentation will stop here. Now you can switch on your mics, and thank you very much, ladies and gentlemen. I want, just because I think it will be the last time when I talk to you as a group, I want to wish you all the best in the exam because I know you can do it. The trick with the math is that you must go there on your own and do those questions on your own, because what you have listened to today gives you what is that you need to do yourself. But if you think that by just listening you can do that, you will see flames in the examination. So to avoid seeing flames in the examination, go there and find time and do this over and over and over again. The trick that I have explained to you, they work in all the derivative, all the integrals that you will do. Thank you so much and have a wonderful evening. And good luck with those that are writing tomorrow. Bye-bye. So everybody must leave.
The line is not clear. I can't hear anything.
You can't hear what? Hello? So you can't hear me? Hello, guys?
We can hear you. We can hear you. I can hear you on my side.
Oh, okay. So if you can hear me, I'm asking for all the guys to just leave the presentation, because if you don't leave it, Dr. Dlamini cannot be able to download the link. So please, let's all leave. Thank you very much. Goodbye.
Bye, sir. Thank you.
Okay, right. MM, can you please go? Thank you. Tavisile, please go. Monaki, Tavisile, please leave the presentation now. Right.